Here is another example of binomial distribution hypothesis testing, but this time we're actually going to do it using critical regions, which once you've actually found it, makes the hypothesis testing a lot easier. And sometimes a question will specifically ask you to find it first, therefore you may as well use it to answer the next question. It's actually just an alternate method to performing a hypothesis test. So the example I have here at the moment is a school estimates the probability that a student gets an A or B to pass in biology exam to be 0.6. So as we go along, it's always worth kind of highlighting what the important information is. So there's a probability of 0.6. The school appoints a new teacher who has never taught this topic before. The head of science is concerned that the A and B pass rate may decrease. Also, this right here is quite important because it will actually tell us which direction to pick when we are doing our hypothesis test. Although all students passed the following year out of a group of 19 students, only 6 got an A or B grade. So what we're going to do to begin with is determine the critical region for our hypothesis test with a 5% significance. Although in an actual exam question it will probably ask you to do a couple of things first. It'll set this out and it will say find the probability of this, find the probability of that, determine what distribution we can use. Here we're jumping straight to the chase and just assuming we already know it's a binomial distribution, and then hence perform a hypothesis test of 5% significance and comment on the head of department's concern, and then find the actual level of significance of the test, which is also something that can be asked. If we're going to come back to this when we have to answer the question in context, but in order to have space to actually work, I'm going to just write the main pieces of information. So, this is the information that we're dealing with. Probability 0.6, we're dealing with 19 students, 6 of them got AB. Is there a decrease? We're testing to 5% significance. We're going to find the critical region to begin with. Now what that actually means, what does 5% correspond to in terms of the number of students? So what I'm going to solve is, because there's a decrease, our hypothesis test will be checking to see if maybe the probability has now gone down from 0.6. So if x can be modeled by the binomial distribution with trials 19 and probability 0.6, what I'm looking at is what is the probability, what is the number, and we're going to call it R for region, what is the number from which the probability of getting that number of students and less, essentially where does that start going under 0.05. But here what I'm trying to figure out is, in general, even if I didn't know 6, at what point would I start worrying? So I'm going to solve this. Now again, we saw this in kind of the example 7 at the end of the binomial chapter. I'm trying to figure out at what point does my data go under 0.05. Now luckily in this case we have less than. What is nice about this is that this is already in the orientation of our cumulative frequency tables. So if I look at a table, all I need to do is figure out where does it go past 0.05. Now very unhelpfully in this case, most likely in an exam you will get much nicer numbers than 19, but it turns out if you look through your tables, you do not actually have 19. It goes directly from 15 to 20, which means that what we have to do is, in this kind of question, we have to use our calculator. This is why I cannot emphasize enough how important this calculator is, because you cannot do this with another calculator. What I'm going to do this time, instead of just randomly trying trial and error, I'm actually going to use the list function. Ideally, what we're going to look at is the probability for 0 students passing, the probability of 1 or less, the probability of 2 or less, the probability of 3 or less, just like we see in a table. However, if I'm dealing with 0.05, I don't actually need to go too far. So instead of doing a list of all 19, we're only actually going to go up to 10 or 11 just in case, and then if that isn't enough, we can always go up further. In the same way as we were doing before, I'm going to go to the distribution, I'm going to go down, and I'm going to use the binomial cumulative distribution. But this time, instead of doing variable, which just gives us one value, I'm going to do a list. And at this stage, you have a table. You just want to write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's go to 10. There we go. And then if you press equals again, it's going to ask you which binomial distribution to use, cumulative again. So we're going to look at n equals 19, and the probability we're looking at is 0.6. And what we get after the calculator thinks for a little while is a list of probabilities. So you can actually skim down, and we can see off the bat that the bit where it crosses over past 0.05 is between 7 and 8. So if I actually write this down on the board, it looks something like this, where you can actually scroll onto the 0.0115 and it will give you the much longer version, because what it's actually done is it's done all the exact calculations itself, which is why it took so long to think. But if I hadn't gotten to 0.05 yet at this stage, I could then go back to the list and add a couple of values. So this stops us from kind of doing a little bit of trial and error, and actually allows us to see immediately where that border is right there, because from here to here, it passes the 5% mark, which means that at x equals 8, I'm over the 5% significance. But as soon as you get 7 or less, we're actually going to start questioning the statistics. That means there's statistical evidence to show that there might be something up. So this is what we call our critical value. This is the first value that actually infringes on that danger zone. So it's the first value inside the 5%, and what we call all of this up until 0 is the critical region. So in order to answer question A, if we go back to the example, question A asks us to find the critical region. The critical region is x less than or equal to 7. So what this allows us to do is no matter what the outcome was at the beginning of the problem, I just have to compare it to that. And this is where B, we're doing the hypothesis test, so the first thing we need to do is say our null hypothesis is that nothing is wrong and the probability is actually 0.6, and our alternate hypothesis is that maybe the head of sciences was right and that there's actually a smaller than 0.6 probability that people pass. So now that we've set these out, all I need to do is compare the 6 I got with my critical region. If I get 6, then 6 is inside my critical region, because 6 is indeed less than or equal to 7. So what we are going to say is there is enough evidence to reject H0. And then what we need to do is then make a statement in context. This is where the non-number values in the question come in handy. If we go back to actually reading the original question, what we're going to use is the head of science is concerned that the A and B pass rate may decrease. So now that we've done the hypothesis test, we can answer this in context. That means that we can say, therefore, the head of science's concerns are founded, and there might be a decrease. So we never want to outright say that there is something wrong, because it's just statistical evidence shows, and it just means further investigation is needed. All we need to do is highlight, is there maybe a problem or is there definitely not? And to the 5% significance, we have tested that there is actually potentially something wrong, and that's essentially where we want to leave it at. Once you've done all this work, the hypothesis test is easy. You just have to compare it to the critical region. The last question that they ask is to find the actual level of significance. And with a one-tailed test, this is actually very straightforward. Essentially what it's saying is, I'm saying 5% significance, but nothing in my actual values is exactly 5%. The smallest value that crosses the 5% is actually 0.0352. So to 3 significant figures, if I want to answer question C maybe here, the actual level of significance is 0.03522 blah blah blah, 3.52%. That right there is the actual level of significance, because there's nothing between that and the first value that actually crosses over the 5%. So I hope that this was clear. Normally you will be able to use the tables, but just in case, we have this extra tool on our calculators. Give it a go yourselves, and good luck.